So let's see, did the recording start? Awesome. Okay, so yeah, just a quick announcement before we get started. In case you weren't here last week, SSD is putting together a team to work on our website. If you want to get started on a beginner level front-end project, but you've never done any kind of front-end development before, this might be a great opportunity for you. As of right now, we're not planning to do anything crazy like React, Redux, or any of those crazy front-end things. We're going to be starting with basic HTML, CSS, some pretty simple features. So if you're really looking for a beginner level project, this might be a great opportunity for you. We're going to have our first meeting right after tonight's workshop right here. So as soon as we're done going through all these slides, we'll come up here, Blake and I and all of you lovely people who are interested, we'll be able to get started. And again, just last chance for anyone to fill out the attendance form if you haven't already. As always, that will help us be able to keep getting pizzas for y'all in the future. All right. So tonight we're going to be talking about a topic that is very near and dear to SSD's heart. With all the different computer science clubs on campus, this is pretty much the single topic that SSD was started over, because this is one of those things that no one ever warns you about in classes, in other clubs, in all of the influencer day in the life of a software engineer videos that you see online. No one ever seems to warn you about this topic, despite it being super relevant to pretty much your day-to-day life in the industry, and that is software design and maintainability. So in a nutshell, software design is basically all about how we blueprint and structure our programs and how we make our code easier to work with over the long haul. And we'll talk more in detail about what that means as we go on. But first, I just want to kind of talk about why it matters. Why do we care about this topic in the first place? This is a topic that can get pretty technical sometimes. We could do like 5 straight workshops on software design topics if we wanted to. So before we get too much in the weeds with anything, I really want to go through some real scenarios that happen in real companies that will show you why we need to care about this. So let's just start off with a question here. I know most of us here probably haven't done a lot of time in industry, but how do we think industry is different from school? We'll take best guesses here. Yeah. They care about making money. You're damn right. Correct. Brian. Yeah, that is a huge one. I would say, yeah, clarifying the requirements, trying to figure out what you need based off those. That's a big challenge. Brian said teamwork. That's a big one. Do we have any other takers here?
Yeah. No, we feel progress. Don't get to like making a frame project a lot of times. Working on some sort of system that other people have already made. I have to maintaining it or adding on features.
That's a huge one. You're working on stuff that people already made, Michael. The requirements change in the middle of development. Oh my God, yeah. Blake. Your team members can be hit by a bus at any time, correct? Like more likely they'll get laid off in one of the thousands of tech layoffs that we've seen in the past year. Did someone else have their hand up? Yeah. There's real life consequences of what you do. Your users are real people who might be depending on your software to get their day-to-day work done, or might even be life and death situations. There might be several people telling you the requirements. They might disagree. That's another huge one. So yeah, Brian. More strict work protocol. It could depend from place to place, but we've gotten a lot of great answers here, and we're about to go over some of those. You guys have a pretty good idea. I like to name some of the biggest differences between industry and school. the three evil C's. So when I say that no one warns you about these are kind of the bad parts of working software development that no one tells you about. So what are they? I like to say they are careless complexity, constant change, and crappy communication. So these are not good things. They suck. But they are a very real part of the software development life cycle that all of us will have to go through. So, other than some nice alliteration, what are these things and how do they make our jobs harder? So first off, complexity. Now, I want y'all to look at this diagram real quick and tell me what this does. Time's running out. 3, 2, 1. User's birthday. Wrong. Okay, so obviously that was a rhetorical question. I'm not expecting anyone to get this. If you did get it just from glancing at that, one, I don't know how you'd be able to read all those words from back there. But two, you should be the one giving the talk instead of me if you could figure out what this is. I think you are, yeah. Are you talking about the little replication clusters right here? Yeah. Yeah, so first major difference between school and industry. This might seem like an obvious one, but real life systems are very complicated, right? I'll tell you right now, this right here is a system design diagram for a large scale video streaming service, right? So something like YouTube, Netflix, Disney Plus, whatever you're watching your movies on nowadays. This is how it might be designed. And as you can see, it is a behemoth. It'll be very confusing trying to work on a system like this, where you have hundreds of engineers involved, a lot of people touching every single change. And it really makes things harder because, for one, learning the code is going to be more difficult, right? Especially if you're someone who doesn't have a lot of technical expertise, it's hard enough just trying to learn how React works or how some new framework they've never used before is. But when it comes to these big systems like this, even experienced engineers who have been in the game for years take a lot of time. Sometimes you go into these companies, they might say it takes an engineer about 6 months to really be productive. And that's really the kind of scale of complexity that we're dealing with here. So learning, just what you're doing, it can be very intimidating when you get started. Another thing that's really hard is making changes, of course, right? Using the whole the bag of wires here. Now, I assume most of us here have been gamers at some points in our lives, and I assume most of us have had a setup that looked like this at some point. Now, for the people who just laughed, I appreciate your honesty. So what's the experience like whenever you're trying to plug in a new wire into one of these, right? It sucks. You can't figure out where the old ones are, where you need to unplug something. If you need to take a wire out to move it somewhere else, you've got to untangle a whole bunch of things. And it takes forever compared to if you just had arranged your wires properly in the first place. Software is exactly the same way. When things get tangled, it takes longer to make changes. It takes longer to figure out where you need to make the changes in the first place. And when you're working against the clock and you're trying to deliver changes on time, that could really set you back. And changes that you think should be simple could take unnecessarily long. And that might lead you to being seen as a lower performer. Your manager might be like, hey, why can't you get this simple change out in time? I just asked you to change the name on this form field right here. Well, I have to unwire this part here and change this, and it depends on this information here. It's a mess. And also fixing bugs, that kind of goes with making changes, but whenever you have something time sensitive, right? Let's say you have a crucial bug in your system that is bringing the whole thing down. Someone here said that one of the ways industry is different from school is that there's real money at stake, right? You're making money from your products. Real people are using your things. They might depend on your app to do their job. And every single second your product might be down or your product has a crucial bug, that's a second that your company is losing money. That's a second that your customers aren't able to access crucial tools that they need. And that's another second that your company's reputation goes down. And as a developer, it is our job to make sure that doesn't happen. So complexity is bad enough, but the thing that makes it even worse, this just multiplies the difficulty of this all, is that software changes constantly. So what you're seeing right here is YouTube from way back in 2005. I'm pretty sure all of us here, we were either like toddlers, maybe even a few newborns. Do we have any 2005 babies here? And welcome. This picture might be older than you, man. Yeah. Yeah, I'm pretty sure I was like 3 when this actually not this picture. This is a screenshot from the Wayback Machine that I took. But this is how YouTube's homepage looked when it first launched. Now, as I'm sure you guys have noticed on all of your favorite apps, the user interface is changing constantly, right? Every year there might be some new update to what you have. And managers are asking for things to be changed. They want to put this button here, add a new feature. Why don't we put some advertisements here? And things just change year after 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 year, and it just doesn't stop. And I'd say around like maybe 2017 or so, YouTube came to be the old current screen we know now. This is what it looks like nowadays. Um, but especially like when we were younger, I was addicted to YouTube from a very young age, so I noticed a lot of the changes here. Companies love to add new features, right? And who's responsible for doing that? The devs, us. However, this is just our homepage, right? I'm sure you guys have seen on the YouTube player in their creator studio, things are changing all the time. On the different apps that you use, Instagram, they're stealing another company's social media features every 6 months. Um, it's crazy. And software, it's really unlike other industries because if you have a car, right? If you're Toyota and you sell a car to someone, ship it out, once that car's out on the road, it's gone. You can't do anything. But software, you can push out updates over the internet at any time. And that means that us as developers are on the hook to be able to keep adding these new features to existing software, basically as much as our stakeholders are telling us to. And when you combine, oh, that wasn't the most recent YouTube. Okay, just goes to show how much this is changing. Um, but when you combine that with how complex these systems be, it ends up being a really sticky situation. So let's come back to that same diagram we had a second ago, right? Now, again, this is a diagram for a video streaming service, just like YouTube. Now, those past 12 images we saw, can someone try to figure out where on this diagram all of those changes would be? Again, if you can read it from here, I'm more so expecting wild guesses. If you can read that from out in the seats, you probably have like supervision. Brian. Oh my God, you actually got it. Yep. Yeah, so it's right here. Correct. Yeah. So all of those changes that you just saw there, they only make up a tiny fraction of this diagram, right? For a lot of these big services that you see, the UI changes that you see that are constantly changing every 3 6 months, those are just the tip of the iceberg. There is so much back-end technology going on behind the scenes that you don't even see, and all that stuff is changing just as fast, if not faster. And for each one of those things, you've got hundreds of developers who are dedicating their time to working on this, keeping it working, and trying to change it with any of the new challenges that might come up. So just take the sheer complexity, the scale of that, and then combine that with how often things change. And that becomes pretty intimidating. Um, how do we deal with that as developers? So again, kind of going over the same point again, but why would we need to change our apps code? I think you guys are probably going to do pretty well with answering this, but I want to hear it from you guys because I trust you guys. You're smart. Exactly. Want to keep innovating, right? Want to keep having reasons to attract new users. Is anyone else? Exactly. Yeah. Um, More new features can often bring in new users, as he just said, for more sales. Oh my God. Can you say that louder for the people in the back? Yeah. Yeah. So again, for the people on Zoom, designers, stakeholders, other people who determine what you have to build often don't know how complicated it is to actually build the thing that they want. Does anyone else want to chime in? Yeah. Exactly. Performance, making changes that will make it cheaper for your service to run. That's something that could cause changes. Bug fixes, a huge one, right? That's a good, honestly, I didn't even think of that. A lot of research and development, right? A lot of the new technologies you see, they take years of effort often behind the scenes before they ever get to the public, right? Chat GPT, which kind of took the world by storm this past fall, had years of machine learning research and development going into it before anything like that ever went public. So we'll go ahead and leave that there. I think y'all pretty much got all of it. So number one, new features, right? Companies love to push new features all the time. Fixing bugs. Again, like we said, every minute that you have a bug live in production is a minute that your users are being hurt, a minute that your company is losing money, and a minute that your reputation is suffering. Another one is security holes. This kind of goes with bug fixes, but is even more serious because obviously, right? Let's say if you're Gmail and you get hacked and everyone gets access to everyone's Gmail accounts, that's all their other accounts compromised, right? And that could lead to things like identity theft, people losing real money. It has, and for you, the company, potential punishment from the government in terms of fines, investigations, other things like that. So if you find a security hole in your software, you need to be able to fix that immediately. And as one person said, scaling or performance, right? If you are building an app that has 10 users as opposed to an app that has 100 million users, you're going to have to build them completely differently in order to scale and be able to handle all that traffic. So again, we've got a lot of good reasons to basically change our code. And then the third major headache, communication. So code is very fickle and precise. Problem is, people are not. And as some of y'all mentioned already, oftentimes people aren't very clear in what they want, and that causes a lot of problems. Let's go through a quick example. Let's say you're a developer, your name is Jesse, and you want to build a web page. So let's say you need to design some options from a list, right? The user needs to be able to select some options. Now, let's say Walter is our product management manager here. He's telling us to do this, and we designed this. So this is a nice list that will allow us to select our favorite restaurant. However, Walter was pretty vague in how he wanted us to design it. He just said, let us select an option from the list. He didn't tell us how he wants us to style it. He didn't tell us what kind of list we want it to be. So, we decided to make a very plain HTML dropdown written in Comic Sans. I'm sure that's very professional looking UX. And I think every front end developer has the urge to do that at least once in their career. But, since Walter wasn't specific, he might come back and say, hey, I wanted it to be a dropdown. And now Jesse's going to get in trouble because he didn't go and specify what he wanted. So don't be like Jesse. He sent Hank to punch Jesse on his behalf. I don't know. I'll make a confession. I haven't actually seen Breaking Bad yet. I promise I will. But yeah, again, vagueness and requirements causes a lot of problems and can force us to go back and have to make unnecessary changes later. Now, another thing that can come up is communication between developers, right? Let's say you have a couple of engineers working on a social media app. Let's name them Eric and Blake. These people are not based off of any real likenesses or anyone who's ever been involved with SSD. So again, they're building a profile feature for a social media app. Imagine something like Instagram's profile page. So Eric is responsible for writing the UI, and Blake is going to be responsible for the code that handles user data. So let's say Eric is writing this function here that renders a profile, right? So right here, he assumes that he's going to get this function called get user profile, which will basically return to him a profile object. Are most of us here familiar with classes and objects? Okay, so yeah, basically just TLDR, a class allows us to group several variables together. So right here, profile would group together certain information like a name, a bio, follower count. Eric assumes that Blake is going to write a function that gives him all of that data in one call. So again, as we can see here, he thinks he's going to get a function that returns a profile object. The thing is, Eric and Blake never actually discuss this. They're just making assumptions here. And that is a good way to ruin your life as a software developer, because now Blake is going to turn around and write a separate function for each field. And now, instead of this single object, Eric has to make a separate function call for each field, which would have been fine if they agreed to that before. But they didn't. And now Eric has to go back and rewrite his code. So again, it's not just that your stakeholders and managers aren't on the same page as development teams a lot, but oftentimes developers might not be on the same page as each other. And that can cause a lot of confusion about what's going to be done and force changes that have to be made later. So we've spent the last 20 or so minutes talking about what can go wrong. What would it look like if things were to go right? What do we want to aim for when we're working in a professional environment? So number one, obviously, maintainability. We've said that words a few times tonight. What does it actually mean? It means that our code is easy to update and fix over time. If I find a bug in my code that is caused by one little section, if I go back to fix it, fixing that shouldn't create 5 more bugs. It shouldn't take 2 days and 5 people to figure out what's going wrong. And it shouldn't take a whole month just to patch whatever went wrong. So again, anytime we want to update existing features or fix anything that might have went wrong, we want that to be as easy as possible. Another thing is extensibility. This is very similar to maintainability. It basically just means it's easy to add new features, right? Eventually, when a product manager, business analyst, UX designer, whoever you have at your company, whenever they come back and say, hey, I want you to add stories to Instagram or something like that, we need to make sure that the system we already have is able to accommodate that without having to rewrite the whole thing from scratch, right? And then finally, readability. So again, it's in the name. Your code is easy to read and understand. You can't update your code base if you can't even read the code that you need to change in the first place. So all 3 of these things here are very important to making sure that your experience as a developer is as seamless as possible and you're able to keep getting your work done at a decent pace. So that brings us into what this lecture is all about, software design. So again, like I said at the very start, software design is kind of similar to building a blueprint, right? If you're building a house, you don't just go into it with a drill and some screws and start putting a bunch of wood together, right? You build a blueprint. You say, I'm going to have this room over here. We're going to have a front door right here. We're going to lay out these measurements. Everything's pretty detailed and you're very specific about it. Same way if you're building a car, right? You have to put together all of your parts. You have to figure out what parts you need, they're going to be made of, who's going to work on this. And if you're working on code, a big app like YouTube, you have to do the same thing. So what's the equivalent of this for software? So software design, our official definition of it is the process of defining a program's specification and structure from a high level. Now, those might seem like a couple of big words down, so let's break this down a bit. A specification is essentially what your application does. It's a bit oversimplified. We'll talk about it in more detail later on, but we're basically saying, okay, what exactly is our program going to do? In no uncertain terms, we need to figure out, we need to get all of our stakeholders together, figure out what is the exact behavior we want. We don't want to leave any ambiguity here. And then the structure here is essentially how our program does it, right? how do we break our system up into different parts? Which parts are going to be responsible for what functionality? How are they going to work together? That kind of thing. So again, you're going to be seeing these two words a lot tonight, the what and the how. So the what and the how, essentially that's what software design is. I like to think about this in more of a three-step process. So again, number one, define exactly what your system does. Leave no ambiguity, right? Figure out, get with all our stakeholders. These are the exact requirements. We need us to do so and so, and write that down somewhere. Now, once you define that, again, you can divide your system into different parts. Ideally, you want the different parts that do different things to be mostly independent of each other. And again, we'll emphasize that more later, but we kind of want to strive for independent when we split our system up. Computer science is all about taking a larger problem and then breaking it down into smaller sub problems to solve. And then once we've gotten those kind of subsystems figured out, we need to figure out, okay, how are those different parts going to communicate with each other, right? So again, you want to define what your system does, divide it into parts based on what they're going to do, and then define how those parts are going to communicate with each other. So software design is an iterative process. If you've never heard the word iterative or iteration before, it's used pretty frequently in tech. It just means taking things one step at a time, right? So imagine you're at a company, very first thing you're going to do is get some requirements. Manager tells you, I want X, Y, and Z, right? So what you're going to do is before you get into any code, you're going to do some software design, right? So again, sit down with your stakeholders, figure out exactly what you want, figure out how you're going to do it, break down everything like that. And then once you figure out the details, you can write your code, right? And after that, your manager can come back to you and say, okay, good job. You can write more features. However, an important step in this process is that oftentimes before we finish our feature, we come back to the software design part. One thing about software is that it changes so much that you can't design a perfect system from the very start. So we need to build our software not just in a way that's anticipated, that's able to anticipate change, but we also need to come back and reevaluate how our designs are working as the system evolves over time. Even when you're working on a feature for the first time before you publish it, you might just write up some code first to get the feature working. And then once you have the kind of your mess of code together, you can go back, look at it and say, okay, how am I going to refactor this so that it's able to fit into our system better and be able to handle future change? So again, you can get product requirements, you can do your software design, and you can write code, but you might come back and do some more software design before you actually finish your feature and go back to step one. So the software design stuff sounds pretty nice. What do you have to know in order to do it? Well, we had our 3 evil C's at the start, which talked about the things that ruin your life as a software developer. Now let me tell you about the 3 blessed P's. And these are kind of 3 elements of software design that will really help you learn more. So basically principles, patterns, and paradigms. So first, principles are basically some general rules and guidelines. If you've ever heard of things like don't repeat yourself, solid principles, those are examples, right? They're general rules that you can follow to basically make your code nicer. Next thing, and yeah, dry, solid, these are some very common ones. Next things are patterns, design patterns, and you guys have probably heard of this before. I know when I took programming 2, they at least mentioned them and went over a couple even. These are reusable solutions to common problems. So patterns such as the singleton, which I know we went over in programming 2, the visitor pattern, which was integral to the PLC project for those who've taken that, and monads, a very frightening design pattern from functional programming land. Again, design patterns are used in common situations, and they often rely on principles. For example, I had a brain fart here. We'll come back to that later, but if you take a look at some of the solid principles, which relate to object-oriented design a bit more, and then look at some of the design patterns, you'll notice that a lot of them deal with common things, right? So the dependency inversion principle, which if you guys don't know what that is, I'm not expecting anyone to understand, influences design patterns such as a strategy pattern, which allow you to basically change the way your program works at runtime instead of hard coding it. And again, that's a bit oversimplified. I always encourage y'all to do some more research later. And the last part here are paradigms, which is essentially a style of programming. So basically, when you combine a certain set of principles and a certain set of design patterns, you get your paradigms. And the three major ones are going to be object-oriented programming, functional programming, and procedural. There are some other lesser-known paradigms, but they're not really relevant. I've only ever worked with code bases. I've worked with one of these three, and most likely you will too. And object-oriented code is what you're working with in classes mostly. So again, paradigms combine principles and patterns in a certain way to kind of give you a certain style of programming. And you might have entire languages that are more geared towards one paradigm or the other. So Java is very object-oriented focused. C is a procedural language. Haskell is a functional language. And if you don't know what Haskell is, I guarantee you most of the people in this room don't. But yeah, these are kind of the three main things that you should look at when it comes to learning software design. Now, the reason I'm kind of breaking it down like this is because there is so much software design content that we can't go over all of these things for every paradigm, for every principle and pattern in one workshop. So this will kind of be a little guideline for you to go and look and see later. Okay, I'm interested in learning more. What things should I be on the lookout for? And everything else we go over tonight is going to be kind of surface level because this is more of an introductory workshop. So let's talk about those introductory concepts. So number one, software design is not a religion. And I really need to drive this point home before like we get into any of the more technical details, because you can absolutely take this stuff too far, right? Remember, we said when we started that we want to fight against complexity, right? Code getting way too complex is really what makes our jobs harder as devs and what makes it harder to make those constant changes that we're required to make. And all of these software design tools are supposed to be things in our toolbox we can use to limit that complexity. But if we overuse it or go crazy, it can make things more complex than they need to be in the first place. So you have to remember that there's always going to be trade-offs, right? Use of too many design patterns or using a principle in a certain place or following it too religiously, even if you need to do something really simple, can make your code harder to read. And that really just defeats the whole purpose, right? So the one thing you have to remember is that rules are not absolute. Generally, the larger scale your problem is, the more likely it is that you're going to need to think of some software design pattern to apply here to keep things manageable. But if you are doing something that involves like a single two-line function, then maybe you can play a little bit more loose with the rules. So each time you make a decision, you're going to be giving up some stuff. There's no silver bullet. Things are not going to be perfect. And really the only way to learn is by experience. So just to kind of show you what I mean, because I've been talking here for a while, I want to show you guys an example of software design gone horribly, horribly wrong. So by a show of hands, who here knows what FizzBuzz is? Okay, pretty good. So for the uninitiated, FizzBuzz is a very simple programming challenge. Basically, you're given a number as input, and if the number is a multiple of 3, you print the word fizz. If it's a multiple of the word 5, you print the word buzz. If it's a multiple of both, you print the word fizz buzz. And if it's none of the above, you just print the number. Sounds like some very simple code, right? Most of you can probably imagine that in your head. This right here is a project on GitHub called FizzBuzz Enterprise Edition. This is basically where we build FizzBuzz with all of the wonderful patterns, principles, and paradigms from the world of software design. And it is beautiful. Let's take a look at it real quick. So this looks like it's a Java project right here. We've got like 10 different folders. What is a serious company, business, Java? I like it. We've got like 6 different interfaces, printers, string printer. I like that. Look, it's like we got a whole interface for like one function here. This is very easy to follow. Don't you guys agree? You see the uncomfortable laughter. You see, obviously, if we were working with someone and we just want to make FizzBuzz and they did this to us, we probably wouldn't be so happy, right? Where are we? FizzBuzz, Java. Okay, void FizzBuzz, int n FizzBuzz upper limit. Where is this number coming from? Do you guys know? I don't know. So just to show you guys how badly this is overcomplicating this problem, let me show y'all what a simple implementation of FizzBuzz looks like. Ta-da, that's FizzBuzz. And I can even prove it works. See, enter number 30, it's a FizzBuzz. Enter another number 7, it gives me 7 because it's not a multiple of either. That's all you needed. So please, please, please do not be too eager to apply any of these principles that you might learn, because oftentimes it's just going to shoot yourself in the foot and make things worse off than they were when they started. A certain acronym that one of my mentors at my internship this summer told me is something called YAGNI. And YAGNI just stands for you ain't gonna need it. All right. So basically what this means is whenever we're working on a project, we want to start simple, usually with the simplest possible solution. And we only want to refactor to these more complicated design patterns when we have a reason to, right? So for example, let's say you are working with constructors, right? There is a design pattern called the builder pattern, which is good whenever you have a constructor that has a lot of fields. And again, if you haven't gotten the object-oriented classes yet, just know this is a design pattern. And this use case right here, right? It's a good example of determining when you want to use one of these tools. We've identified a clear need for this in our code base. So we're going to use this here. Now, a bad reason to use it would be because someone told you it was cool, or you read an online article where someone said, oh, you need to start using these design patterns today, but they don't give you any context where to use them or when you should use them. It's just kind of like they're telling you they're cool and it makes you a better developer, but they don't give you any detail about when you use them. If you can't justify using it, don't use it. That is a big thing that will save you a lot of grief and time of moving on. All right, so now that kind of tirade is over, let's talk about another concept called cohesion. Cohesion is a pretty simple idea. It means that related functionality should be placed close to each other in our code. The goal of this is that if we're working on features for user profiles, for example, I don't want to have to jump through 12 million different files just to figure out what I'm doing, or I don't want that functionality to be split across 5 functions in a single code file that has 20 different functions in it, right? That's confusing. So this could go on the level from individual lines of code to functions to even your higher level architecture. I think I just saw Varun here. How's it going? Former president of SSC just tuned in. Yeah, shout out to him. So yeah, cohesion is the idea that related functionality should be placed together. This is an example of how you might group your folder structure if you're working on a project. So let's say if you're working on a social media app, you might maybe want to group all of your code by features. So you could have one folder with DMs. This has all of your code related to direct messaging, another one for your feeds, for individual posts, users. They're split by feature, right? It makes sense. You're separating things by their concerns. Another way to do it is splitting things by their technical concern. So let's say you have an app where you might have one area of your code that handles the user interface. You might have a part of your code that's responsible for talking to the database, another part of it for dealing with network requests. The idea is we want to split things up, as we said earlier. And ideally, when we split those things up, things should be split in categories that are related to each other. I'd say this is probably the most self-explanatory slide in this whole deck. And a big one, dependencies. So a dependency is a pretty simple concept, right? If one code uses another piece of code, it is dependent on the second piece of code. So this is also known as coupling. If you ever hear someone say code is coupled, that means there's a dependency. Here's a very, very simple example of this. Let's say we have a class called Vector2D. Now, as you can see, this just has two numbers, an X and a Y. If anyone here has ever done game programming, this is how we might keep track of an object's coordinates in our game world. Kind of just like X and Y positions on a graph when you took math class, same concept. So let's say if we have another class for a player, right? And we want to know what is that player's position on the map. We might use that vector 2D class to demonstrate that. So in doing this, the player class has a dependency on the vector 2D class. And this is important to recognize because changes in that vector 2D class are going to affect any class that uses it, including our player class here. And this is a pretty simple example here, right? We really wouldn't need to do any complicated software design stuff for this. But imagine you have a bigger class that has a lot of functionality, it has a lot of functions, and you suddenly need to make a change somewhere. Let's say this has 10 different classes that use it, and you make a change to one of these variables. Let's say you want to change an int to a float. Well, if you're using that float in 10 different classes, what are you going to do? Well, you're going to have to go by hand and change all 10 of those classes, and figuring out where everything needs to be changed is going to be hard because you probably forgot it since the last time you did it. Or maybe it was another developer who wrote the original code and they left the company and now you're on your own. It sucks. So we have to be very careful thinking about dependencies. And the last thing we really want is a big ball of mud, right? When things get tangled in your systems, they become harder to understand. They become slower to work with because you got to jump from place to place to place to place to place to see what's going on. And certain changes you make can affect other parts of your code unexpectedly. Now, this sounds a lot like the problems that we were talking about earlier, don't they? Where we talk about unnecessarily complex code bases where things are harder to find and work with. One of the main points that I want y'all to take home from this whole talk tonight is that if your different parts of your system become too interdependent on each other, that can be the biggest cause of complexity in a lot of systems. And that is oftentimes what will slow you down and make everything harder to do. So we need to intentionally think about what parts of your code are we going to allow to be dependent on other parts of our code. And in general, earlier when I said we want our different parts to be as independent as possible, this is what I mean. Again, a big takeaway, we want to divide our systems into independent parts when we're designing them and then define clear boundaries between them, right? The more involved one class is in another class's business, the more opportunities there will be for a change in one class to force a change in another one. Of course, we can't make them totally isolated from each other, right? Different parts of our code have to be communicate. Otherwise, you're not going to have a system. So, how do we actually make this dream of independently designed software a reality? So this brings us to our kind of last major part for this workshop, interfaces and specs. So we talked about earlier the concept of the what versus the how. You're going to see the whole main point of this section here is we want to separate the what from the how in our applications. Now, what do I mean by that? So let's say you wrote a piece of code. We'll call it the supplier. Basically, this is a piece of code that some other part of our program is going to use. So we could call that other code the client. The names aren't too important here. The concept is we write a piece of code and some other code is dependent on us, right? How do we keep that other piece of code from basically being forced to change by any changes we make? Well, one way is that we need to make sure that the other piece of code or client here does not know the internals of how our code works, right? Or that they know as little as necessary. Because simply put, the less they know about our code, then the less they need to change whenever we have something that changes. So they shouldn't know how we're working under the hood. We need to basically only allow them to know what functionality we can provide them. Now that's kind of abstract, so I'm going to go ahead and give you all an example right here. And almost forgot this part. So yeah, the whole supplier thing, we can separate that into two parts, an interface and an implementation. So basically an interface is kind of a middleman between ourselves and any class that is depending on us. Basically, instead of the class directly interacting with us, an interface lists all of the public functionality that we have available, and it tells our client, hey, you can use this function. This is the type it's going to give you, but it doesn't reveal any internal variables we might have. It doesn't even tell you how the function works. And our implementation is private to us. Other classes don't know anything about it. So for an example here, let's say you're hungry and you want a burger. Let's say you go to Krusty Krab for some food. So when you go to a restaurant to order, you just talk to Squidward here, tell him you want a Krabby Patty. He sends the order back to the kitchen, and then 2 minutes later, he hands you back your burger. And that's all there is to it, right? Now, us as the client, as a customer, we don't know or care about the internals of the kitchen, right? So we don't care what ingredients went into the burger. We don't know what stove they use. We don't know what kind of grease they use to fry it. We don't know what kind of oven they use to cook it. We don't care about any of that. We just walk up and say, give me this item off the menu. I want my food. And they give it to us. And this is very important because let's say Mr. Krabs gets cheap one day and says he wants to replace SpongeBob with the old fry cook. Well, ideally, that shouldn't make a difference for us as a customer, right? We should be able to go in to the cashier, say we want a burger, and get the exact same burger that we got yesterday. And nothing that happens on the back end over here should affect us. So, and we all know that's how it works at restaurants, right? Each time you go to McDonald's, it's probably a different person giving your order and a different person cooking the burgers than it was last time. You don't notice. And code should work the same way, especially when you're talking about large separate parts of a system. We want to make our code such that if we are asking a code to do something for us, that we don't know what that internal code has to do in order to give us a result. And by not even interacting with that part of the code, when that internal piece of the code makes changes, we don't have to worry about it because we're not looking at it in the first place. So real quick, before we go any further, does anyone have any questions regarding this? I know this is kind of an abstract concept here. Like, then we replace them with another fry cook because we can. Problem solved. Yeah, so again, this whole concept of interfaces basically define what your code does, and they allow you to use a piece of code indirectly without knowing how that code works internally. And again, this is what allows us to separate the what from the how. And this is, again, one of the core concepts for tonight. So real quick, I want to go over a couple of different types of interfaces that you might see in programming. Oh, my bad. Yeah, so interfaces define what code does, and they allow you to use code indirectly. So yeah, and again, there are a few different types of interfaces that we'll go through here real quickly. Does everyone have this down? Who wanted it? Cool. So first, class interfaces. By a show of hands, who here has worked with languages like Java or C# before? Okay, so a lot of you are probably familiar with these already. So, and remember, interfaces define what our code does. An interface for a class defines what a class does. It defines what methods the class has. So let's say we want to build a notification system here, right? Basically, whenever we have an event in our app here, let's say we want to send a notification to someone, right? Like, for example, have you guys ever had like those Discord bots on your servers that, I don't know, when a new game on Steam comes out, it makes a post that lets you know, hey, this new game came out. Have any of y'all used something like that before? Yeah. And, of course, if you have a phone, you've used a notification system before, right? So this is an example here. Let's say we're building a notification system. Here we have an interface that says we want to be able to send a notification. We just give it the message and it sends it out. But it doesn't really give us a lot of details, right? It just tells us that it's going to send a notification. So what we can do is we can write a class that implements this interface. Basically, this is a contract that says when the class implements that interface, the class promises to have every function that is listed here. So if I have the send notification function in this interface, then the class that implements it needs to have that function too. So this class right here is called Slack notifier. So basically what this is going to do is it's going to send our message to Slack, right? It'll be connected to some kind of Slack bot, post a message in a channel, whatever. So we just give it the message and it posts it to Slack. But what if we wanted to change it, right? I don't know how many of y'all use Slack, but I'll be honest, I don't check Slack that often. It's basically just corporate Discord. But I know that all of y'all use Discord because that's how we do all of our communications for SSD. So let's say we want to build another notifier for Discord. Well, we can just make another class that implements notifier interface. And we have the same send notification function here. And again, it takes in a string message. It works the same way from the outside, but on the inside, it's doing different things. Now, why do we care about this? Well, for one, it might work differently trying to send a message from Slack to Discord. I know some of y'all here might have tried to work on Slack bots or Discord bots before. They work differently, right? You have to call different things. You have to set up different libraries. And if you're writing a system where you want to be able to have a notification system for both, you don't want to go through the hassle where, oh, I wrote a Slack notification system already, but I want to add Discord notifications too. Everything's all tangled up. How do I separate that? So here with the notifier interface, we can use the same interface to send either a Slack or a Discord message. Let me show you what that looks like. So let's say we've got a function here where we can create an event. Basically, it'll save that event to some imaginary database here, and then it will send our notification. Now, if you notice here, this notifier thing, it's not a concrete class. This function doesn't know what kind of a notification it's going to be sending. But because right here, this function promises that it's going to give you a class that sticks to the notifier interface, the function can trust it, right? We know just whenever we call this notifier thing, this message is going to go somewhere. And that makes it really easy to swap these out. So let's say at first we want a Slack notifier, right? So we make a Slack notifier here, and then we create an event and we say, here is the Slack notifier. Make this event and then send it to a Slack channel somewhere. But then let's say we change our mind, say no one uses Slack except old people. Let's send it to Discord instead. With this interface, all we have to do is just change the notifier like this, and then put it back into the exact same function. And again, because both the Slack notifier and Discord notifiers implement the same interface, it can call the send notification function no matter what. And we know it's going to be going to somewhere that accepts notifications. Now, why, again, what we want to do is, as we can see here, it makes it really easy to make important changes like this that could otherwise force you to make changes in a whole bunch of different files, right? Let's say we had this Slack system for a long time before, and we wanted to introduce a new Discord notification system. Well, you could work, as long as I implement the same interface, you could work on the Discord notifications behind the scenes, and you wouldn't have to change anything for all the other code that's already relying on the Slack notifications. And if you want to be able to send a message to both Slack and Discord, well, you just add this line of code here that makes it call the Discord notifier afterwards. So again, this really makes it easy to not just swap out behavior, but to also keep that separation. Because again, the notifier here, it doesn't know how the notifier class works internally. And that, again, is one of the keys to how we can kind of keep functionality separate. So again, before we go on, does anyone have any like questions or clarification about what's going on here? We all good? Mm-hmm. Exactly, the interface. Yeah, exactly. So compared with our last example with the Krusty Krab, basically Squidward would be the interface, the guy who's taking our order. He's a middleman between us and the kitchen, and kind of the concrete classes that we have before. Oh, went the wrong way. Concrete classes that we have before are kind of the cooks. They're responsible for doing our dirty work. So again, those are class interfaces. Those are a good way to keep separation from within a program within the same app. Now, oftentimes, however, we're going to want to use code that someone else wrote. And this is when we're going to use something called an API. Now, API stands for Application Programming Interface. You guys have probably heard of this acronym before. And it's basically a special type of interface that lets you use code from another program. So there are a few different kinds of APIs. We've all probably used one before. Number one, libraries and frameworks, right? Anytime you're using library code that someone else used, for example, a React component, that is an API that the developers of React have exposed for you to use their code. Now, all of React's internal details, such as the virtual DOM, knowing when to re-render, those things are handled internally and you don't look at it. But you worry about the components and how those are built, because that is the API that React gives you. Similarly with SFML, right? For the programming final projects, or Pygame from Programming 1, they're both similar libraries. They render stuff to screens. They give you functions to draw stuff to a screen. You don't worry about how you're interacting with your computer's GPU. You just tell it, hey, draw me a rectangle at this position, and it handles it for you. Another example are network APIs. So anything you're writing where basically you call another program that's running over a network, it does some work and it sends the data back to you, that's an API. And this is kind of the most common form of API. This is actually typically how a front end will talk to a back end. And we will be doing a back end workshop in a few weeks if you guys want to learn how to build one of these. But again, that's a super common one. And then finally, system calls are a huge example. Pretty much anything you do on your computer has to go through the operating system. So for example, writing a file, you don't directly interact with your computer's file system when you do that. Windows exposes some functions that you can call, and either by calling the Windows functions directly or by calling a library that calls one of Windows functions, you tell Windows what you want it to do, and it will manipulate those files for you. And again, it keeps you from having to worry about how an entire operating system works under the hood, so that way we can just focus on writing our app. And it's also good for security too, because can you imagine if any like app offer just had access to your whole file system? It'd be pretty bad. So next we'll talk about specifications. Now, we mentioned this word earlier. Basically, a specification is a detailed description of a system's interface. So again, interfaces kind of describe what our code does. Specifications really describe that in much more detail. So specification is where you kind of want to break down the exact requirements for what your code does, right? When you're writing your specification at a start of a project, this is when you want to get your stakeholders sit down and say, okay, we need to do X, Y, and Z. This is when you really want to think through all of the specifics, think through all the edge cases. Think, okay, do you want this button to be green? What happens when my screen is full screen? How do you want it to look when it's on a mobile display, when the user has only half the browser open? Break things down into exacts, and this is the stage where you want to get basically consistency from your stakeholders and come to an agreement. And oftentimes this is going to require a lot of communication to be done. You have to talk with a lot of people doing this. Contrary to popular belief, software engineering is not a job where you can just kind of sit by yourself and be antisocial. Communication is very important, and this is exactly why. Because it's oftentimes very hard figuring out exactly what your clients want. So making sure you get all that settled before you start writing code is crucial. Now, again, just like an interface, a specification is external. It describes how the system appears to users. Now, again, a user can either be a person, as it is with most apps that you use, or it can be another program. For example, if you're writing a backend, your front end might be the user interface for the same app. So specifications typically don't describe how the program works under the hood unless you are specifically told it has to work a certain way. So again, it's kind of analogous to the interface, except it's more detailed and it's documented somewhere. And also, it will typically outline what kind of outputs might be necessary. Again, if you're writing an API, for example, for other developers to use, they need to know, hey, what functions can I use? What are they going to return? And what inputs am I required to give this as a user? And again, like we said, the users here can be people or code. So again, a specification, again, it's not in the code itself. Typically, you'll usually might have it in a document somewhere. And we'll actually go ahead and do a quick demonstration of this right now. Um, so if you guys have ever looked at documentation before while writing code, I assume almost everyone here has. It's pretty much impossible to write code without doing it. You're looking at a specification. So this right here is a Java collections interface. This basically describes all of the data structures that you see in Java. So if you've ever used arrays in Java, array lists, hash maps, anything like this, there's like 20 data structures here. This document right here would tell you everything you need to know as a user of that code. So here, as you can see, we have a lot of the functions that are available to us. It tells us the output types, the input types, and as you notice clearly, it doesn't tell us how it works under the hood, right? We don't see the internal body for the isEmpty function. We don't know what code is inside there. It just tells us what we need to give it and what we're going to get. And again, we'll go over this more in a second, but please make sure you read the documentation like this clearly when you're looking at a library. Another example of an API might be Discord. So we know we had that example earlier of a Discord notification bot. If you wanted to actually go and build that, this is where you would look. This is documentation for the Discord API, which allows you to write your own programs that can do things like post messages to Discord. If you want to do that, you would go here. As you can see, it tells you what kind of network calls you would need to make to hit their API. It tells you what you need, the fields that it will return. Everything you need to know should be in the specification. So again, if you're using someone else's code, you want to read their specification, wrong tab. And if you're writing code for someone else to use, you need to make sure you have a specification for them. And no matter what kind of user you have, you do need to determine the exact requirements before you write it. So again, a lot of this is the same concept. We want to separate the what from the how. We've had different terms here, such as APIs, interfaces, specifications that describe what those interfaces do. We say those interfaces are contracts between the people who use them and the people who write them. Idea is that we want to separate what our external users of our code know from how that code works internally. And again, that is, if you don't remember anything else from tonight, that's kind of the core idea of this presentation, because that is what allows us to split our programs up into independent parts where we can make changes in one piece of our code here and not have it destroy the entire rest of our program. So again, hide our internal details from external users. If you're a certain subsystem in your code, hide your internal details from other parts of your program. And again, like we said earlier, don't be too religious about this. You don't want to hide necessary information, right? If there is some kind of piece of data that another piece of code needs to know in order to do its job, then by all means, make that publicly available. Again, you'll learn more about the kind of nuance that software design needs as you get more experience, and experience is really the only way. So one more quick thing on this note, interfaces might not reveal everything that you need to know about a function. So let's say we have a simple square root function here. As you can see, it just takes in a floating point number is basically just a decimal, and it gives you another float that should be the square root of the number that you pass in. So does this tell us everything that we need to know about this function? How could we break this function? I'll get, yeah. Exactly, a negative number. So yeah, oftentimes the input types for an argument don't tell you everything you need to know. You know, if this was in an interface for a class and I just read the interface in the code, it wouldn't tell me that. So, what are some ways that we can prevent those kinds of mistakes from happening? From both the side of the person using the code and from the person writing the code. That's a good one. Yeah, so in languages that allow you to do that, that is a good option to do. I'm not sure if Python lets you do that. Full disclosure here, I really don't use Python. But again, if you have some kind of data type that only lets you put in positive numbers, that's a good one. Does anyone else have anything? Documentation, huge one. This is the exact kind of information that needs to be outlined in your spec, right? So I'm just gonna go ahead here. So again, if you're the person using the code, what you can do is read that specification, right? Um, the writers of Java didn't put all this info here for us, just for it to go to waste, right? I understand we might be lazy sometimes, we might not want to read all that, but false assumptions are often a cause of a lot of bugs in code. So anytime you're relying on someone else's code, make sure you actually understand what it's doing. Come back here. There we go. The window vanished for a second. Another thing you can do is not make assumptions as before. And if you're the person writing the code, again, make sure you have proper data validation. So ideally, if someone puts in a negative number in here, this function should throw an error right away. And the reason we want to fail fast is because we don't want some corrupt data to be going around through our program. So, if a user tries to do this and they run their code, ideally it should fail right away. Tell them, hey, this is what went wrong right here. You passed in a negative number to a square root. And then also, this information needs to be included somewhere, even if it's not inside the interface that's in the code. If it's not in a comment somewhere, put it in your documentation, make it so that it's somewhere where someone else could find out about this. And there are a lot of kind of gotchas that you could look at like this. We've talked about more examples about this in our previous software design workshops. If you want to see more examples of how mistakes like this can happen, check them out on our YouTube. So just look for anything called Intro to SSD or software design workshops from previous semesters, and we'll have more examples like this. So I only want to leave out like one last point. And we know that software design is really helpful for for maintaining your application and making things easier while you work, but they also help you learn. Now, could someone here take a quick guess on why would knowing software design help you learn new tools faster?
Yeah, I can go. Um, it basically helps you recognize patterns faster, and also generally the design patterns that are used in one are researched enough, and if you understand one of them, it's easy faster to learn other things as well.
Yeah, exactly. So again, all of these libraries or frameworks you might use, they use these design patterns too, right? So for example, if you're learning React, React borrows a lot of concepts from functional programming. So a lot of things in React that might not make sense to you if you've never done functional programming before would be a lot easier to grasp if you knew it. Similarly, if you're working with Java libraries, again, Java is a very strict object-oriented language. If you use Java libraries, you're probably going to be seeing words like factory or builder or a whole bunch of other design patterns that you've never heard of before. And you might not have any idea what they're doing or why they're there. But if you know the software design principles, you'll read that and you'll understand what it is. And that can really help you learn these new tools faster. It can also help you learn new code bases faster as well. If you, this summer, I worked on a backend that relied heavily on functional programming. It used a framework that was designed around the entire concept of keeping side effects away from your main logic, which is one of the principles of functional programming. And because I understood that, it was a lot easier to learn the code, and I became a lot more productive a lot faster. So again, just getting even a basic handle on these principles. You don't have to be an expert. You don't have to be able to name every single design pattern, but having an awareness of them can really help you learn things a lot faster. And that's really just kind of the last note I want to leave y'all with for tonight. So it's a few more things. Reminders real so our workshop is done. These are going to be our workshops for the next few weeks. Save the dates for whatever you're interested in. Also the AI Days hackathon is coming up. This time it's actually going to be over a full weekend, unlike last year where it was like one day. There will be up to $20,000 in prizes. Go ahead and scan that QR code if you're interested. It is real money. I can vouch I won $400 in last year's competition. And you guys will have to beat me again if you want some money. I'm just playing, but that money is real. And it's also a great opportunity to get a small project on your resume. I know a lot of you guys are underclassmen who are trying to get some experience, and more info will be right there. And lastly, hackathon updates. We will not have our hackathon in Marston this weekend since it will be closed for homecoming. We're thinking maybe the CIC dungeon, but we're actually going to discuss that with our web dev group, which is going to meet right now, right here. So before we sign off for the day, do we have any questions, closing notes, anything? All right. Hopefully you guys are feeling a bit smarter than you came in. Have a good night. To everyone online, thank you for coming. Have a good night. That was awesome.
Eunice, we're staying over on the same call, right?
Test 1 2. Test 1 2. Okay, hey web dev people, come on up here. I don't think there's that like I don't think there's an entire horde of us, so we'll gather up. Yeah.
Come up here.
Sit. It's a little awkward, but yeah. No, I don't know.
Oh, okay.
I'd rather